3.5 binomial theorem. So expand and simplify the binomial a plus b cubed, and we're going to do foiling, okay? So in grade 10, we would have, oh, that's supposed to be a b. We would have expanded this by doing a plus b times a plus b times a plus b, okay? Our rule is 2 at a time. So to expand a plus b times a plus b, we're going to get a squared plus 2ab plus b squared. And we're going to expand that into a plus b. So let's multiply everything by a first. I get a cubed plus 2a squared b plus ab squared. Now let's multiply everything by b plus a squared b plus 2ab squared plus b cubed. And then now we simply collect like terms. So a squared b's, I have 3 of them. And then ab squareds, I have 3 of them. Okay. Then I have an a cubed and a b cubed. So that's how we would expand with foiling. Here's the thing though, this exponent here is only 3. So we're only expanding this 3 times. The issue is that if this number is like 5 or 8 or 10, the bigger it gets, the more tedious the expansion becomes. So what we do is we use binomial theorem and we use Pascal's triangle in order to expand. Okay, so this is exactly what I just said. When we expand a plus b to the n, it becomes laborious as n increases. So let's learn what the binomial theorem is to make expanding easier. The method used to expand any power of a binomial expression in this form. So technically what ends up happening is we see 3 patterns here, okay? So let me highlight. N choose 0, n choose 1, n choose 2, all the way to n choose n. And we can use either Pascal's triangle or we can actually use the choose function. Now, a to the n, a to the n minus 1, a to the n minus 2, all the way down to a to the 0. And then b to the 0, b to the 1, b to the 2, all the way up to b to the end. Okay, we do have a Riemann sum expression for this. It's just the sum of all integers from 0 to n, and then it gives the general form. So let's take a look at the patterns. The degree of each term in the binomial expansion is n. What that means, I'll delete this, is taking a look at n plus 0, that equals n. N minus 1 plus 1 equals n. N minus 2 plus 2 equals n. 0 plus n equals n. So whatever the powers add to, they are always going to add to n in the basic expansion. Okay, exponents on this first term, which we call a, right, from the a plus b, they're going to decrease. They're going to go from n to 0, and we can see that here. And then exponents on the second term, so we call the second term b in that expansion, they go from 0 to n. So they're increasing. And then the coefficients of each is going to be in the form NCR. Okay, starting at 0, going all the way to n. Okay, you can say from 0 to n. Okay, and throwing this out there, there are n plus 1 terms in each binomial expansion. So whatever that exponent is, say the exponent's 10, there would be 11 terms. If the exponent's 15, there'd be 16 terms. Okay, sometimes when we're multiplying and actually expanding, we have to use exponent laws. So just a quick recap. When 2 numbers are multiplied and they have the same base, we add the exponents. And then we're going to review power rule. So when we have a power raised to another power, we multiply the exponents. So let's actually apply binomial theorem. And I'm going to show you how to actually pattern these. So we have the same question as above. Let's start with the choose function. So we're going to say 3 choose 0, 3 choose 1, 3, choose 2, 3, choose 3. Okay, now we start with we continue with the first term A, times A choose 3 times A to the 3, A to the 2, A to the 1, and then A to the 0. Now let's pattern the B. B to the 0, B to the 1, B to the 2, and B to the 3. And if you take a look, there are 4 terms here, which is the 3 plus 1. Now let's actually expand. I'm going to show you 4 items that you're always going to be able to cancel out. So 3 choose 0 is just 1, and 3 choose 3 is just 1. It's going to be the first and the last terms in the Pascal's triangle. We know that they're 1. Also, any base to the exponent 0 is 1, so we can cancel out the b to the 0 and the a to the 0. Now let's simplify. We have simply a cubed, and then 3 choose 1 is 3, a squared b stays, 3 choose 2 is 3, a b squared, and then we have b cubed left. So that one's expanded with very, very little work. Now let's take a look at an expansion with a little bit more work. B, 2x plus 1 to the exponent 5. So let's start with the choose function. 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. And if you count, there are 6 terms. Now, 2x. 2x to the 5, 2x to the 4, 2x to the 3, 2x to the 2, 2x to the 1, 2x to the 0. I would put those in brackets because the exponent applies to both the 2 and the x. Now, 1 to the 0, 1 to the 1, 1 to the 2, 1 to the 3, 1 to the 4, and 1 to the 5. Okay? So let's get rid of anything that is just a 1. 5 choose 0 and 5 choose 5 go away because they just are 1. Now 1 to the 0, 1 to the 1, 1 to the 2, 1 to the 3, 1 to the 4, 1 to the 5, those all cancel to 1. And then this 2x to the 0 also cancels to 1. Now let's rewrite this. Simplify. So 2x to the exponent 5. So 2 to the exponent 5 is 32, and then we get x to the 5. Okay, 5 choose 1 is 5, times 2x to the exponent 4 is going to be 16x to the 4. Remember that 4 has to apply to the 2 as well. Okay, 5 choose 2 is going to give us 10. Now, 2 to the exponent 3 is 8, and then x cubed. 5 choose 3 is also 10. Right, we're going to have that symmetry there. 2 squared is 4x squared. 5 choose 4 is 5. And then we have 2x. Okay, and then we have plus 1. So all of these in the last term cancel out to 1. We still have to include that 1 because 1 times 1 times 1 equals 1. Now let's actually simplify. We get 32x to the 5. Now we say, okay, what's 5 times 16? 80. 80x to the 4. What's 10 times 8? 80x to the 3. What's 10 times 4? 40x squared. What's 5 times 2? 10x plus 1. And that's the expansion. Okay, last one. 3x minus 2y to the exponent 4. So let's expand the coefficients first. 4 choose 0, right, because we're basing it on this. 4 choose 1. 4 choose 2. 4 choose 3. 4 choose 4. And if you take a look, there are 5 terms, n plus 1. Okay, let's pattern the 3x. 3x to the 4, 3x to the 3, 3x to the 2, 3x to the 1, 3x to the 0. Now let's pattern negative 2y. Negative 2y to the 0, negative 2y to the 1, negative 2y to the 2, negative 2y to the 3, negative 2y to the 4. Okay. Before we calculate anything, let's get rid of 4 choose 0 and 4 choose 4. And then anything to the exponent of 0 just cancels out to a 1. And now let's expand. So 3 to the exponent 4 is 81. So I get 81x to the 4. 4 choose 1 is 4. 3 cubed is 27. X cubed. And the negative 2 to the 1 is going to be negative 2. And then we have y. Now, 4 choose 2, we get 6. 3 squared, we get 9, and then we have x squared. And negative 2 squared, we get positive 4, and then y squared. 4 choose 3, we get 4. 3x to the 1, we just get 3x. Now, negative 2 times negative 2 times negative 2, right? So the negative 2 cubed is going to give us negative 8, and then we have a y cubed. Now, negative 2 to the exponent 4 is 16, y to the 4. Okay, and now let's simplify more. The 81x to the 4 is done. Okay, let's multiply 4 times 27 times negative 2. Okay, I get negative 216. And then x cubed y. We'll go on that. Let's multiply the 6, the 9, and the 4 now. I get positive 216. And then we have an x squared and a y squared. And then we have 4 times 3 times negative 8. I get negative 96. And I have xy cubed, and the last term is already done. 16y to the 4.